Hello, and welcome. In this series, we are going to embark on a detailed journey into the heart of modern artificial intelligence, the models that power applications like ChatGPT. At the core of this revolution is a technology often referred to by a simple three-letter acronym, GPT. You've seen these letters everywhere, but what do they truly signify? Understanding them is the first and most critical step to understanding how these remarkable systems work. So let's break it down, piece by piece, starting with the G. The G stands for generative. This means the model's primary purpose is to create something new. It's not just classifying data or recognizing patterns, it's generating original content. This could be text, like writing an email or a poem, but as we'll see, it can also be code, images, or music. The key idea is that the model isn't retrieving answers from a database. It's constructing them, word by word or pixel by pixel, based on the patterns it has learned. It is a creator of information. Next, we have the P. This stands for pre-trained. This is perhaps the most economically and computationally important part of the acronym. Pre-trained means that before we ever ask the model a specific question, it has already undergone an intensive, foundational training process on an immense and diverse dataset. Essentially, a huge portion of the public internet, books, and other text. This initial training is general purpose. The model isn't taught to be a legal expert or a poet. It's taught the fundamental patterns of language, grammar, facts, and even reasoning styles. This foundational knowledge can then be adapted to specific tasks later in a much faster process called fine-tuning. And finally, the T. This is the technological core. The T stands for transformer. The transformer is the specific type of neural network architecture, the engine, that makes all of this possible. Introduced in 2017, it revolutionized how machines process sequential data, like the words in a sentence. Its key innovation, a mechanism called attention, allows the model to weigh the importance of different words in the input when generating an output, enabling it to understand context and nuance in a way previous architectures couldn't. We will spend the bulk of this series deep inside this architecture, understanding exactly how it works. So there we have it. Generative, pre-trained, transformer. When you combine these three ideas, a generative model that creates new content that has been pre-trained on a vast corpus of general knowledge and is built upon the powerful transformer architecture, you get the foundation for the most capable AI systems in the world today. Each piece is essential. Throughout this video series, we will explore each of these pillars in great detail. We'll start by building up the fundamentals of machine learning, then dive into the mechanics of the transformer architecture, and finally see how the generative process truly comes to life. Now that we have our roadmap, let's begin our journey with the foundational principles of how machines learn in the first place. And that brings us to the three core ideas packed into the name generative pre-trained transformer. To truly understand how these models work, we're going to deconstruct this name piece by piece, starting with the first and most important letter, G, for generative. What does it really mean for a model to be generative? It means it has the ability to create new content, in this case text, that didn't exist before. But it doesn't do this by having ideas or consciousness. Instead, it follows a surprisingly simple, yet powerful, iterative process. Let's build a visual model of this process. Imagine we give the model an initial piece of text, a prompt, like "the cat sat on the." This prompt is fed as an input into the model, which for now we can think of as a complex black box. Its job is to do one thing: predict the very next word. Now, here's the crucial part. The model doesn't just spit out the one word it thinks is best. Instead, it considers thousands of possible words from its vocabulary and calculates a probability score for each one. The output is a full probability distribution. We can see here that Matt has a very high probability, around 60%. Floor is a reasonable alternative, with a 20% chance. Hat is less likely, but not impossible. The model has learned from reading trillions of words that, in this context, Matt is the most statistically likely follower. Next, the model needs to pick one. For now, let's assume it uses a simple strategy and just picks the word with the highest probability. So it selects mat, but the process doesn't stop there. If it did, we'd only ever get one word. This is where the magic happens. The model takes its own output and appends it to the original input. This is the feedback loop. The process is autoregressive asterisk, which is a technical term meaning it regresses or depends on its own previous outputs. The new, longer sentence, "The cat sat on the mat," now becomes the input for the very next step. The model's context has been updated, and now it simply does the exact same thing again. It takes this new prompt and predicts the next asterisk token. What's most likely to follow "the cat sat on the mat"? Well, a period to end the sentence is extremely likely, and end to continue it is also possible. The model calculates the probabilities and again, it selects the most likely option, the period. This selected token is fed back, appended to the sequence, and the process repeats, word by word, token by token. Once this loop is established, it can run very quickly. The model generates it, then a, fluffy, Persian, and just like that, by repeatedly asking what comes next and feeding its own answer back into itself, the model has generated a coherent, novel sentence from a simple prompt. This core autoregressive loop is the engine that drives the generative power of GPT. Now that we have a solid mental model for this generative process, let's look at the second letter, P, for pre-trained. How does the model know that mat is more likely than hat in the first place? That's what we'll explore next. In our previous discussion, we saw that GPT models are generative, meaning they can create new text. But this raises a fundamental question. How does a machine, a piece of software, know what to write? How does it understand grammar, facts, and the subtle nuances of human language? The answer lies in the second part of its name, pre-trained. A model, when first created, is like a brain with no memories or knowledge. It's an empty vessel. We can see its structure, its potential for learning, but its internal parameters, the millions or billions of numbers that will eventually define its intelligence, are essentially random. It knows nothing. This is the untrained model. If you were to ask it to generate text, you'd get complete gibberish, a random sequence of words and characters. So, how do we fill this vessel? We make it read. Not just a book or 1,000 books, but a significant portion of the entire digital world. This is the pre-training phase. We expose the model to a vast, general dataset. Think of it as the collected works of humanity. A massive library containing websites from the internet, countless books, scientific articles, news reports, and more. This colossal stream of information is fed into the model. As it processes this text, word by word, sentence by sentence, something incredible happens. It begins to learn the patterns. It's not memorizing the text. Instead, it's learning the statistical relationships between words. It learns that they is often followed by a noun. It learns that questions often start with who, what, or why. It learns the rules of grammar, context, and even rudimentary reasoning, all by observing how we, as humans, connect ideas. The random, meaningless pathways inside the model begin to organize. They light up, forming a complex, interconnected web of knowledge. The model is developing a foundational understanding of our world, as represented in our writing. After this immensely resource-intensive process is complete, we no longer have an empty vessel. We have a pre-trained model. It is now a generalist. It has a broad, comprehensive knowledge base. It can discuss history, explain scientific concepts, write poetry, and even generate computer code, all because it has learned the underlying structure of human language and information. This general knowledge is incredibly powerful, but sometimes we need an expert, not a generalist. What if we want a model that specializes in a very specific task, like analyzing legal contracts or writing medical diagnoses? We wouldn't want it to get creative and write a poem in the middle of a legal brief. This is where the final step, fine-tuning, comes in. Instead of a vast, general dataset, we now use a much smaller, highly curated and specific dataset. For instance, a collection of thousands of legal documents. We feed this specialized data into our already pre-trained model. Notice, we aren't starting from scratch. We are building upon the vast foundation of general knowledge the model already possesses. The model uses its understanding of grammar and reasoning and applies it to this new, narrow domain. As it processes the legal texts, a specific part of its knowledge network becomes more refined, more specialized. It learns the unique vocabulary, the structure of legal clauses, and the patterns specific to that field. The general knowledge of language is still there, but a region of expertise is now sharpened to a razor's edge. The result is a fine-tuned model. It's like a general practice doctor who has gone on to complete a surgical residency. They still have all their general medical knowledge, but they now also possess deep, specialized expertise. This fine-tuned model can now perform its specific task, like identifying risks in a contract, with a much higher degree of accuracy and relevance than the general pre-trained model ever could. So, this two-step process is the key. Pre-training on a massive, general dataset gives the model its foundational intelligence, and optional fine-tuning on a small, specific dataset allows us to adapt that general intelligence to create powerful, expert tools for countless applications. Now that we understand how these models are trained, we need to look under the hood at the engine that makes all of this possible, the transformer architecture itself. What are these pathways, and how do they actually allow information to flow and context to be understood? Let's dive into that next. So far, we've unpacked the first two letters of GPT. We know generative means the model creates new text, and pre-trained means it learns from a massive dataset before being fine-tuned. That brings us to the final, and arguably most important, letter in the acronym, the T. The T stands for transformer. And the transformer is not just a concept, it's the specific, powerful, and revolutionary neural network architecture that serves as the engine for GPT and nearly all modern large language models. To understand why the transformer was such a breakthrough, we first need to look at what came before it. For many years, if you wanted to process sequential data like text, you'd likely use a recurrent neural network, or RNN. The idea was intuitive. It processes a sentence word by word, and a loop in its structure allows it to maintain a sort of memory of the words it has seen before. An evolution of this was the LSTM, or Long Short-Term Memory Network, which was a more sophisticated version designed to remember information for longer periods. For a time, these were the state of the art. But both of these architectures shared a fundamental limitation, especially when dealing with very long texts. They struggled with what's called long-range dependencies. Think of it like a game of telephone. An RNN processes the first word, passes its understanding to the second, which passes an updated understanding to the third, and so on. By the time it gets to the 500th word, the critical meaning of the first few words can be diluted or lost entirely. This sequential, one-by-one processing made it very difficult for the model to connect a word at the end of a long paragraph back to a key concept mentioned at the beginning. This was a major bottleneck. To achieve true language understanding, we needed a model that could grasp the context of the entire input at once. And in 2017, researchers at Google introduced the solution in a landmark paper titled "Attention is All You Need." They proposed the transformer architecture. Unlike an RNN, the transformer doesn't process text in a strict, linear sequence. Instead, it's designed as a deep stack of identical processing blocks. It can look at all the words in the input sentence or document simultaneously. But how does it know which words are important to which other words? This is where the secret sauce comes in. The core innovation of the transformer is a mechanism called self-attention. We will dedicate several future scenes to unpacking exactly how attention works, because it's a deep and fascinating topic. But for now, the key idea to grasp is this. The attention mechanism allows every word in the input to directly look at and weigh the importance of every other word. It builds a rich network of contextual relationships, no matter how far apart the words are. The worded in a sentence can directly attend to the noun it refers to, even if that noun was hundreds of words earlier. This completely solves the long-range dependency problem. This single, powerful idea of parallel processing with self-attention is what makes the transformer so effective, and its power isn't limited to just generating chat responses. This same fundamental architecture is so versatile that it has become the backbone for a huge range of incredible AI applications. It's used for machine translation, converting languages with unprecedented accuracy. It powers text-to-image models, turning a written description into a beautiful piece of art. It's at the heart of modern voice transcription and text-to-speech systems. Summarization, code generation, drug discovery. The list goes on and on. All of these diverse capabilities are unlocked by this one core architecture. So, when we say GPT, we are talking about a generative, pre-trained model built on this incredibly powerful and versatile transformer engine. Now that we have a high-level view of all three parts, it's time to open up the black box. In the next scene, we'll begin our deep dive into how the transformer actually processes information, starting with the very first step, turning words into numbers. In our journey to understand the T in GPT, the transformer, we first need to grasp a concept that underpins all of modern AI. It's the fundamental shift in how we teach computers to solve problems. To see what I mean, let's explore two different ways to tackle a seemingly simple task: teaching a computer to recognize a cat. On one hand, we have the traditional approach, programming with explicit rules. Imagine you're the programmer. You'd have to think of every possible rule that defines a cat. You might start by telling the computer to check for whiskers. If the image has whiskers, great, but what if it doesn't? Or what if a dog has whiskers? Okay, so you add more rules. Does it have pointy ears? Does it say meow? Is its body a certain size? What about tail length? What about different breeds? A Persian cat looks very different from a Sphinx. You can see the problem. This web of rules becomes incredibly complex, brittle, and will inevitably fail as soon as it encounters a cat that doesn't fit your predefined checklist. It's like trying to write a recipe that can cook every dish in the world. It's impossible. Now, let's look at the other side. This is the world of machine learning. Instead of giving the computer a long list of rules, we give it a model. For now, just think of this model as a box. And inside this box are millions of tiny, adjustable dials. In technical terms, these dials are the model's parameters, or weights. They are the internal configuration of the model that determines its behavior. Crucially, we don't set these dials by hand. So how does the model learn what a cat looks like? We don't give it rules, we give it data. We show it thousands or even millions of pictures that we've already labeled as cat. As the first image enters the model makes a guess. Let's say it gets it wrong. It then gets a small signal telling it, that was incorrect. In response, it slightly adjusts some of its internal dials. Then, it sees the next image. It makes another guess. Maybe this time it's a bit closer. It gets another feedback signal and adjusts its dials again. This process, known as training, is repeated millions of times. The model isn't being told why something is a cat. It's never given the rule, look for whiskers. Instead, by adjusting its parameters over and over in response to labeled data, it learns the patterns, textures, and shapes that, in combination, signify cat. It forms its own internal, incredibly complex representation of what a cat is, a representation far more nuanced than any human could program by hand. This is the core difference. The old way is brittle and built on explicit human instructions. The machine learning way is flexible, and the model learns its rules implicitly from the data itself. This single idea, that models learn from data instead of being explicitly programmed, is the engine that drives everything we'll discuss. It's how a transformer learns language, and it's the foundation upon which we'll build our entire understanding. In our last discussion, we framed machine learning models as systems that learn from data by tuning internal parameters. But what do those parameters look like, and what are they tuning? To understand that, we need to zoom in and look at the fundamental building block of almost all modern deep learning systems, the artificial neuron. Let's build one from scratch. A neuron, at its core, is a simple computational unit. It starts by taking in some information, which we call inputs. Here we have 3 inputs, which we'll label x1, x2, and x3. These could represent anything: the brightness of pixels in an image, the values of a stock on consecutive days, or numerical representations of words in a sentence. These inputs are fed into the main body of the neuron. Now, the neuron doesn't treat all inputs equally. It assigns an importance or a strength to each incoming connection. We call this a weight. A high positive weight means this input strongly excites the neuron. A large negative weight means the input strongly inhibits it. And a weight near 0 means the input is mostly ignored. These weights are the primary tunable parameters we talked about. They are what the model asterisk learns asterisk. So, what happens inside the neuron? The first step is simple. It calculates a weighted sum. It multiplies each input value by its corresponding weight and adds them all together. But there's one more ingredient. The neuron also adds a special, independent parameter called a bias. You can think of the bias as the neuron's innate tendency to be active or inactive, even before it considers any of the inputs. A high bias means the neuron is predisposed to activate, while a low bias means it's predisposed to stay quiet. This bias is also a learnable parameter. Let's write out the full calculation. The result of this linear step, which we'll call z, is the sum of each weight times its input, plus the bias. So, W1 times X1, plus W2 times X2, and so on, finally adding the bias B. If this were all a neuron did, it would just be a simple linear equation. But the real power comes from the second step, a nonlinear activation function. The value z is passed through this function, which squashes the output into a well-defined range. A very common choice is the sigmoid function, which looks like this. No matter how large or small z is, the sigmoid function will always squeeze the result, which we call y hat, or the neuron's activation, into a range between 0 and 1. A value near 1 means the neuron is firing strongly. A value near 0 means it's inactive. This nonlinearity is what allows networks of these neurons to learn incredibly complex patterns, far beyond what simple linear models can do. Let's make this concrete with some numbers. Imagine our inputs are 1, 0, 0, 5, and -1, 0, and let's initialize our weights and bias to some starting values. Right now, with these parameters, the weighted sum z is 0, 25, and the final output is about 0, 56. Now for the most important part. Watch what happens as the model learns by adjusting just one parameter. Let's increase the first weight, W1, from 0, 5 to 2, 0, making the neuron much more sensitive to the first input. See that? As the weight increases, the weighted sum z rises significantly. On the graph, this pushes the point to the right, up the steep part of the curve, and our final output y hat gets much closer to 1. The neuron is now firing strongly, all because one parameter was changed. Now, let's see the effect of the bias. Let's keep the weights as they are and dramatically decrease the bias from 0, 5 down to -2. And there you go. Even with the same inputs and weights, lowering the bias has pulled the entire calculation down. The value of z becomes negative, and the output y hat drops close to 0. The neuron has been biased towards being inactive. This is the essence of a single artificial neuron. It's a simple, two-stage computational unit whose behavior is governed by its weights and bias. The process of deep learning is all about finding the perfect set of these parameters across millions or even billions of such neurons to solve a specific task. In the next scene, we'll see how these individual neurons are stacked together in layers to form a deep neural network. In the last scene, we saw how a single artificial neuron takes in information, processes it, and produces an output. It's a simple but powerful building block. But the true magic of deep learning isn't in one neuron, it's in how we organize vast numbers of them. First, we don't just use one neuron at a time. We arrange them into a group called a layer. Think of a layer as a rank of processors, all ready to look at the input data simultaneously from slightly different perspectives. Now, to give the network the ability to learn complex patterns, we don't just use one layer. We stack them, one after another. A deep neural network is, quite literally, a network with depth, meaning it has multiple layers. We start with our first layer, then we add another, and finally, we add a layer at the very end to give us our result. Notice this final layer can have a different number of neurons depending on the specific task. This structure has specific names that you'll hear all the time. The first layer, which receives the initial data, like the words of a sentence, is called the input layer. The final layer, which produces the model's prediction, like the next word in that sentence, is the output layer. And all the layers in between, These are the hidden layers. They are hidden because we don't directly interact with them. This is the engine room of the network, where the bulk of the computation happens and where the abstract patterns and features are learned. Now, here is the most crucial part. These layers aren't isolated. Every single neuron in one layer is connected to every single neuron in the next layer. This creates an incredibly dense web of connections, allowing information to be mixed and transformed in very complex ways as it passes through the network. So, what does it look like when the network is working? When we feed data into it, a process called forward propagation occurs. The information, represented here by a pulse of light, activates the input layer. It then flows along every connection to the first hidden layer, which processes it. Then it flows to the next hidden layer, being transformed again. Until finally, after passing through all the hidden layers, it reaches the output layer, giving us our final result. This directional flow, from input through the hidden layers to the output, is the fundamental operating principle of these networks. Each layer takes the output of the previous one, reevaluates it, and passes it on. But how does this flow of information actually lead to learning? How does the network know how to transform the data correctly? That has to do with the strength or weight of each and every one of these connections, which is what we'll explore next. In our previous discussions, we've built up a solid understanding of how deep learning models, these intricate networks of neurons and weights, learn from numerical data. They are, at their core, magnificent mathematical machines, fluent in the language of numbers. But this brings us to a fascinating and fundamental challenge. The goal of a model like GPT is to understand and generate human language. It has to work with sentences, with ideas, with nuance and context. And on the other side, we have our neural network, which only understands vectors, matrices, and probabilities. It doesn't know what a cat is, or what it means for one to have sat. So, the single most important question we have to answer before we can go any further is this: how do we bridge this gap? How can we translate the rich, symbolic world of human language into the rigid, numerical world that a neural network can process? Trying to feed words directly into a neural network is like trying to explain a poem to a calculator. It simply doesn't have the right kind of inputs. We have the domain of language and the domain of math. They seem incompatible. The secret, the magic of natural language processing, lies in a systematic process of translation, and that process begins with the very first, most intuitive step. Before we can do any complex math, we need to break the sentence down into manageable pieces. We can't treat the entire sentence, "the cat sat on the mat," as one single thing. We need to look at its components. So the first thing a transformer does is chop the input text into a list of, well, for now, let's just call them pieces. Each word is separated out from its neighbors. This process of dicing the input text into a sequence of these pieces is called tokenization, and each one of these pieces is called a token. In this simple case, each token is a word. The is a token. Cat is a token. Mat is a token. This list of tokens is the first structured representation of our original sentence. Now, you might be thinking, okay, they're separated, but they're still words, not numbers. How does this help? And that is the perfect question to ask. Tokenization is only the first step in a two-part process to solve our language-to-math problem. We've broken the sentence into a list of tokens. The next critical step, which we'll explore in the following scene, is to convert each of these tokens into a list of numbers, a vector. This next step is called embedding. But for now, remember this. Every single time you interact with a large language model, this is the first thing that happens under the hood. Your question or prompt is broken down into a sequence of tokens, preparing it for its journey through the mathematical heart of the transformer. And that entire, powerful architecture begins with a surprisingly simple but crucial first step. In this scene, we'll dive into that first step, tokenization. Before a transformer can perform any of its complex reasoning, it must first understand the input text. But computers don't read words and sentences like we do. They operate on numbers. Tokenization is the process of converting a piece of text into a sequence of numbers the model can work with. Let's start with a simple sentence. The cat sat on the mat. The most straightforward way to tokenize this is to simply split it by the spaces. The model first breaks it down into a list of tokens. Each word becomes a distinct token. This is called word-level tokenization. It's simple, and it works well for common words. But what happens when the model encounters a word it has never seen during its training, or a very complex word, or even a typo? If our dictionary of known words is fixed, we have a problem. We need a more flexible system. This is where a more clever approach comes in. Subword tokenization. Let's consider a more complex word, like the word tokenization itself. A simple word-level tokenizer might not have this exact word in its vocabulary if it's rare, but it has likely seen the parts that make up this word many times. So, instead of treating it as one unknown unit, the tokenizer breaks it down into smaller, more manageable, and more common subword units. In this case, it might become token and ization. Notice the ## symbols in front of ization. That's a special marker used by many tokenizers to indicate that this subword is the continuation of a word, not the beginning of a new one. This allows the model to learn the meaning of prefixes, suffixes, and root words independently, and then reconstruct the meaning of a complex word like unbelievably. This is incredibly powerful. It allows the model to handle a virtually infinite vocabulary with a finite number of subword pieces. Okay, so we've broken our text into these subword tokens, but we're still not at numbers yet. How does the model convert these strings, token and ##ization, into a format it can use for mathematical operations? For this, the model relies on a predefined dictionary, which we call its vocabulary. Think of it as a massive lookup table created during the pre-training phase. This vocabulary contains every single unique subword token the model knows, and each one is assigned a unique integer ID. So, the tokenization process concludes by looking up each token from our text in this vocabulary and replacing it with its corresponding ID. The token might be assigned ID 11,632, and the subword ##ization might be ID 3,869. So, the word tokenization is transformed from a string of characters into a sequence of two integers. 11,632, 3,869. This is the final output of the tokenization step. Our entire input text, no matter how long or complex, is now represented as a sequence of numbers. These numbers are just identifiers, though. They don't carry any intrinsic meaning about the words they represent. The number 11,632 doesn't inherently mean token any more than 3,869 means ization. Giving these numbers meaning is the job of the very next step in the transformer architecture, the embedding layer, and that is exactly what we will explore in the next scene. In the last step, we broke our input sentence, the quick brown, into a sequence of numbers, or tokens. We ended up with the ID 26, 504, and 238. But right now, these are just arbitrary numbers. The number 504 has no inherent relationship to the word quick. For the model to perform any meaningful computation, it needs to understand what these tokens represent. How do we infuse these simple integers with the rich meaning of language? The answer lies in the second step of our process, embedding. To do this, the model uses a special, massive lookup table called an embedding matrix. Now, this isn't just any random table of numbers. This matrix is one of the most important learned components of the model. During its pre-training on trillions of words, the model painstakingly adjusts every single value in this matrix. Its goal is to create a unique numerical signature, a vector, for every single token in its vocabulary. These vectors are designed so that words with similar meanings are represented by vectors that are close to each other in a high-dimensional space. The geometry of this space captures the semantic relationships of language. So, how does the lookup work? It's remarkably straightforward. The model takes the first token ID, 26. It uses this number not as a value to do math with, but as an address or an index. It goes to the embedding matrix and looks up the 26th row. This row is the embedding vector for our first token. It's a list of numbers that now represents the token in a rich, meaningful way. While we're only showing a few numbers for clarity, in a real model like GPT-3, this vector would have over 12,000 dimensions. Let's pull that vector out. And that's it. We've converted the integer 26 into a meaningful vector. The model now does the exact same thing for every other token in the sequence. Next is 504. It looks up the 504th row and pulls out its corresponding vector. And finally, token 238. And now, the process is complete. Take a moment to see what we've accomplished. We started with a simple sequence of meaningless integers, and through this embedding lookup, we have transformed them into a sequence of rich, high-dimensional vectors. Each of these vectors now carries a huge amount of information about its corresponding token and its relationship to all other tokens the model has ever seen. This sequence of vectors is the input that the main transformer blocks will now operate on. They are the fundamental currency of meaning inside the network. With our input now encoded into this powerful format, we're ready to see how the model actually starts to understand context. That happens in the next crucial component, the self-attention mechanism. In the last part, we established that transformers convert words or tokens into long lists of numbers called embeddings. A crucial question follows from this. What do these numbers actually mean? Are they just random identifiers? The answer is not only no, but it reveals something profound about how these models perceive language. To understand this, we need to stop thinking of embeddings as just lists of numbers and start thinking of them as coordinates, points in a vast, high-dimensional space. We need to explore the geometry of meaning. Imagine a space like this one. While a real embedding space might have thousands of dimensions, we can visualize the principle in just 3. Each axis represents some abstract feature of meaning that the model has learned from the data. We don't name them ourselves, the model figures them out. Now, let's place some words into this space, based on their embedding vectors. Here, every word has a unique position. A key principle of this space is that distance equals semantic similarity. Words like cat and dog would be close, while cat and rocket would be far apart. But the truly remarkable property isn't just about distance, it's about direction. The relationships between words are encoded as vectors. This is famously demonstrated with the word analogy task. Let's look at the relationship between man and king. In vector terms, we can find this relationship by subtracting the vector for man from the vector for king. This arrow, this vector, represents that difference. You can think of it as a royalty vector. It captures the concept that separates a man from a king, the addition of monarchy, power, and a crown. It's a direction in the space of meaning. Now for the amazing part. What if we take this same concept of royalty and apply it to the word woman? In vector arithmetic, that means we start at woman and add the royalty vector. Watch as we move this vector, without changing its length or direction, and place its tail at the point for woman. Where does it point? It lands precisely on the vector for queen. This is astonishing. The model, simply by processing text, has learned to organize its internal representation of words such that vector arithmetic mirrors the analogies in our language. King is to man as queen is to woman. This geometric structure is the foundation of a transformer's ability to understand and manipulate language. It's not just matching patterns, it's learning a map of concepts. This principle of semantic geometry applies to countless relationships, verb tenses, country capital pairs, and more. It's this rich, structured embedding space that the rest of the transformer architecture, which we'll explore next, operates on to perform its magic. So far, we've taken our raw text, broken it into tokens, and converted those tokens into meaningful numerical vectors called embeddings. These embeddings are the rich, context-aware inputs that our model will now process. But where do these vectors go? They enter the core processing unit of the entire system, a sophisticated and powerful component that is repeated over and over again. This entire unit is called a transformer block. In a model like GPT, you might have dozens of these blocks stacked one on top of the other. The output of one block becomes the input for the next. For now, let's just focus on the journey of our data through a single one of these blocks. Inside, we find two primary subcomponents, two main engines that do the heavy lifting. The first is the masked multi-head attention mechanism. This is the star of the show, and we'll dedicate several upcoming scenes to it. For now, think of it as the collaboration hub, where tokens look at each other to exchange information and build up a deep understanding of context. Below that is the feed-forward network, or MLP. This is a more traditional neural network component. After the tokens have gathered context from the attention layer, the MLP performs further processing on each token individually, allowing the model to think more deeply about the information it has gathered. Now, let's trace the path of our embedding vectors as they enter the block. The first thing that happens is that the vectors pass through a component called layer normalization, which we see abbreviated as LN. Think of layer normalization as a way to keep the data tidy. As vectors pass through many layers of computation, their numerical values can explode or vanish. Layer norm rescales the data within each vector, keeping the signals stable and making it much easier for the model to learn effectively. It's a crucial stabilizing mechanism. After normalization, the vectors enter the attention module to be processed. But here is where one of the most important innovations of this architecture comes into play. A deep network with many layers faces a potential problem. As information passes through complex transformations, some of the original, raw information from the input can get lost or distorted. How do we ensure the network doesn't forget where it started? The solution is elegant. We add a shortcut or a bypass route known as a residual connection. A copy of the original input vector from asterisk before asterisk it entered the attention module is sent around the module, and is then added directly back to the output of the attention module. This addition ensures that the output of this stage always contains the original signal plus the new, transformed signal. The network gets the best of both worlds: the complex, contextualized output from the attention layer, and a clean, an unaltered copy of the input. It makes training deep networks dramatically more stable. This combined, information-rich vector isn't ready for the next stage just yet. We see a familiar pattern. The result of the addition is immediately passed through another layer normalization step. This add and norm sequence is a fundamental motif of the transformer. You'll see it after every major subcomponent. Now, this fully contextualized and renormalized vector flows into the feed-forward network for the next stage of processing. And what do you think happens after the MLP is done? Exactly the same pattern. The output of the MLP is combined with a residual connection that bypassed it. They are added together, and though we don't draw the final LN block here for simplicity, you can imagine it's there. It's add and norm all over again. This final vector, which has been enriched by both attention and deep processing, is the final output of this transformer block. It's now ready to be passed as the input to the next, identical transformer block in the stack, where this entire process will repeat, adding ever more layers of abstraction and understanding. This block is the fundamental building block of the entire GPT model. Now that we understand its high-level architecture, we're ready to zoom in. In the next scene, we will finally open up that masked multi-head attention box and see how tokens actually talk to each other. In our last segment, we saw how raw text is broken down into tokens and then converted into meaningful numerical vectors through an embedding layer. Each token now has a starting representation, but it's a representation in isolation. It lacks context. To build the deep understanding needed for complex tasks, these tokens need to talk to each other. They need to understand their relationships within the specific sentence they are in. This is where the magic of the transformer really begins, with a mechanism called self-attention. To build an intuition for this, let's look at a sentence. The robot picked up the red ball because it was heavy. As a human, you likely understood that instantly, but for a machine, there's a critical ambiguity here. What does the word it refer to? Is it the robot that was heavy, or the ball? Our real-world knowledge tells us it's probably the ball. But how does the model figure this out without that knowledge? Bookmark mark equals a/. It does so by learning to pay attention. The token for it needs to gather context from the rest of the sentence to clarify its own meaning. To do this, it effectively looks at every other token in the sentence, we can visualize this process. The it token essentially asks every other word a question. How relevant are you to helping me understand my own meaning in this specific context? It forms a connection to every other word, but not all connections are equal. Based on what it learned during its massive pre-training phase, the model assigns each of these connections an attention score, a weight that signifies importance. Let's visualize those scores. Watch closely. The connection to ball becomes incredibly strong and bright. The connection to heavy is also quite strong, as heavy is the reason for the clause. The connection to robot is much weaker, and the connections to other words like the or up are very faint. By weighing these connections, the model has built a new, context-rich representation for it. This new vector for it is now saturated with information from ball and heavy, effectively resolving the ambiguity. It knows it refers to the ball. Bookmark mark equals b/. Now, this isn't just a special trick for pronouns. This process of self-attention happens for every single token in the sentence, all at once. Each word looks at all the other words to enrich its own meaning. For example, let's consider the word robot. To fully understand what robot means in this sentence, it's not enough to know the dictionary definition of a robot. The model needs to know what this specific robot is doing. So it pays attention to the other words, and you can see where its attention is focused. It pays very close attention to the verb picked up, because that's the action it's performing. It also pays strong attention to ball, the object of that action. The meaning of robot is now contextually updated to be the agent that picked up the ball. Bookmark mark equals c/. In a real transformer block, this happens for all words in parallel. Each one is generating its own set of attention scores. If we were to visualize all of these connections at once, even faintly, you'd see a dense web of information exchange. This web is the heart of the transformer. It's a dynamic, content-aware system for routing information between tokens, allowing the model to build up an incredibly sophisticated, layered understanding of the text. So, the core intuition is this. Self-attention allows each word to create a new version of itself by blending in weighted information from all the other words in the sequence. But how are these attention scores actually calculated? It's not magic, it's linear algebra. To understand that, we need to introduce 3 new vectors for every token: the query, the key, and the value. And that is precisely what we will break down in the next scene. Bookmark mark equals d/. In the last part, we built an intuition for self-attention as a process where words in a sentence look at each other to gather context. Now, in scene 15, we're going to roll up our sleeves and examine the precise mechanics of how this happens. This is where the abstract idea of paying attention gets translated into concrete mathematics. Let's focus on a single word from our sentence: the machine is thinking. We'll track the journey of the word thinking. Like every other word, it first gets converted into an embedding vector, which we'll call x4. This vector, x4, contains the initial, context-free meaning of thinking. To start the attention process, the model needs to create 3 specialized versions of this vector. It does this using 3 dedicated weight matrices, which are learned during the model's training. We'll call them WQ, WK, and WV. Think of these matrices as learned lenses. Each one takes the original embedding and projects it into a new space, giving it a specific role for the attention calculation. First, the embedding x4 is multiplied by the WQ matrix. This produces the query vector, which we'll call Q4. The query acts like a question or a probe. It's the part of thinking that will go out and actively seek relevant information from the rest of the sentence. Next, x4 is multiplied by the WK matrix. This creates the key vector, K4. The key acts like a label or a signpost. It's the version of thinking that announces its own properties, ready to be seen by other words' queries. And finally, x4 is multiplied by the WV matrix. This gives us the value vector, V4. The value vector holds the actual content or meaning of the word. This is the information that will ultimately be passed on to the next layer if this word is deemed important. So, from one input vector, we've generated 3 distinct vectors, each with a unique purpose: the query to ask, the key to be matched against, and the value to be shared. This happens for every single word in the input sentence. Now, let's see how they interact. We'll keep the query for thinking, our Q4, and bring in the key vectors for every word in the sentence. The machine, is, and thinking. The first step is to determine how relevant each of these words is to our target word, thinking. How do we measure relevance between two vectors? With a dot product. The model takes the query from thinking and calculates its dot product with the key from the first word, the. The resulting number or score represents how much thinking should focus on the. A higher score means higher relevance. This score is the first entry in our list of raw attention scores. Next, it repeats the process. The query from thinking is compared with the key from machine. This gives us our second score. Notice this score is much higher. Intuitively, this makes sense. The concept of a machine is highly relevant to the act of thinking in this context. The process continues for every word in the sentence. Q4 is dotted with K3 for is. And finally, Q4 is dotted with its own key, K4, for thinking. A word always pays some attention to itself. What we're left with is a list of raw, unnormalized scores. These scores tell us the raw similarity between our query and every key, but they're not very useful yet. They can be any number, positive or negative. We need to turn them into a clean, interpretable format. First, a small but important technical step from the original attention is all you need paper. The scores are scaled down by dividing them by the square root of the dimension of the key vectors. This is a stabilizing factor that helps the model train more effectively, preventing the dot products from growing too large. Now for the crucial step, normalization. We pass these scaled scores through a function called softmax. The job of the softmax function is to take a list of arbitrary numbers and transform them into a probability distribution. This means two things. Every output number will be between 0 and 1, and all the output numbers will sum up to exactly 1. These new values are our final attention weights. They are the percentages of attention that the word thinking will distribute across the entire sentence. You can see here that machine receives 88% of the attention, while the other words receive much less. We now have our attention weights. We know who to pay attention to and by how much. The final step is to use these weights to actually aggregate the information. To do this, we bring in the value vectors for every word. Remember, these contain the actual substance of each word. The process is now straightforward. Each value vector is multiplied by its corresponding attention weight. The value vector for machine, V2, is multiplied by its high weight, 0, 88, so it contributes significantly to the final result. The vectors for the, is, and thinking are multiplied by their small weights, effectively shrinking their contribution. The final step is to sum up all of these weighted value vectors. This sum creates a new vector, which we'll call Z4. This vector, Z4, is the new, contextually aware representation for the word thinking. It is a blend, a weighted average of all the information in the sentence, filtered through the lens of attention. It started as just the embedding for thinking, but now it has absorbed the highly relevant context from machine. This Z vector is what gets passed up to the next layer of the transformer. So, to recap the entire flow, for a given word, we generate a query, a key, and a value. The query is compared to every other word's key to produce scores. These scores are scaled and passed through softmax to become attention weights. And finally, these weights are used to create a weighted sum of all the value vectors, producing a final, context-rich output vector. This entire, intricate dance of vectors is the self-attention mechanism. It's what allows the model to dynamically build relationships between words and form a deep understanding of the input text, a foundation we will see used again and again as we explore the rest of the transformer architecture. In the previous section, we developed a deep intuition for how a single self-attention mechanism works. It calculates a set of scores to determine how much focus each word in a sequence should place on every other word, allowing context to be shared and integrated. But language is incredibly complex. A single sentence can contain layers of meaning simultaneously, grammatical structure, causal relationships, pronoun references, and more. Is one attention mechanism, one perspective on the sentence, really enough to capture all of this richness? The answer the original transformer paper proposed is a definitive no. A single attention head might become very good at one specific task, like tracking subject-verb agreement, but it might completely miss other, equally important relationships. To solve this, the transformer architecture doesn't just use one attention mechanism. Bookmark mark equals a slash, it uses several in parallel. This is the multi-head part of multi-head attention. We literally create multiple, independent copies of the attention mechanism. In the original paper, they used 8 heads. Here, we're showing 4 for clarity. Now, the most crucial detail here is that these heads are not just identical copies in operation, they are independent in learning. Each head has its very own set of learnable weight matrices, its own query, key, and value projection matrices. So head 1 has its own weights, head 2 has a completely different set, as do all the others. Because their parameters are separate, during training, they are free to specialize and learn to pay attention to different kinds of patterns and relationships within the input data. Let's make this concrete. Imagine we feed the model this sentence. Now, let's watch what our different heads might learn to focus on, all at the same time. Perhaps head 1, shown with the blue arrows, specializes in basic grammatical structure, linking articles like the and the to their corresponding nouns, robot, and apple. Meanwhile, head 2 in green might learn the more complex task of pronoun resolution. It correctly figures out that the word it refers back to the robot, not the apple. This is a critical piece of context. Head 3, in teal, could be focusing on action-object relationships, connecting the verb ate to the object apple. And head 4, in gold, might capture properties, linking the adjective rusty back to the robot it describes. You can see how each head provides a different, valuable sub-analysis of the sentence. No single head had to learn everything, they divided the labor. Okay, so now the model has 4 separate, specialized analyses. What does it do with them? It needs to combine this information back into a single, unified representation. The first step is simple. Each head produces its own output vector, which we've been calling Z. The model then takes all of these output vectors and concatenates them, essentially just stacking them together into one large, combined vector. This concatenated vector now contains all the rich, parallel information captured by every single head, but it's also a bit unwieldy and likely too large for the next layer of the network. So, there's one final step. This combined vector is passed through one final, learned linear projection layer, represented by this matrix WO. This layer's job is to distill all that concatenated information back down to the model's standard vector size, mixing the specialized insights from all the heads into a single, coherent, and powerful output vector. And that is the complete process by having multiple heads attend to the input in parallel, each specializing in different features, and then intelligently combining their findings. The transformer builds a far more robust and nuanced understanding of the data than any single attention mechanism ever could. This multi-head block is a cornerstone of the transformer's power, and we'll see exactly where it fits into the overall architecture in the next section. So, after our multi-head attention mechanism has done its job, each token's vector is now rich with contextual information gathered from all other tokens in the sequence. But gathering information is only half the battle. The model now needs a dedicated space to actually think about this new information, to process it, find deeper patterns, and compute more complex features. This is where the second major component of our transformer block comes into play. Following the attention sublayer, every single one of these context-rich vectors is passed, one by one, into what's called a feed-forward network, or FFN. Now, despite the fancy name, this is fundamentally a simple, 2-layer neural network, but its structure is very specific and serves a crucial purpose. Let's trace the journey of a single token's vector through this network. The first thing that happens is that the vector enters the first linear layer. The primary job of this layer is to take the input vector, which has a dimensionality of D model, and project it into a much larger space. Typically, this inner layer dimension, called DFF, is 4 times larger than D model. Why do this? You can think of it as giving the model a much larger workspace. By expanding the representation into a higher dimensional space, the model has more room to work with the relationships between features, allowing it to learn and represent much more complex patterns that might have been tangled together in the lower dimension. But a linear transformation Even an expanding one isn't enough. If we just stacked linear layers, the whole network would just be one big, simple linear function. To give the model true computational power, we need to introduce nonlinearity. And that's the job of the second step, the activation function. In transformers, the standard choice is the rectified linear unit, or ReLU. Its job is incredibly simple. It looks at every single number in our expanded vector and replaces any negative value with 0, leaving positive values untouched. This simple act of clipping negative values is a nonlinear operation, and it's what allows the FFN to approximate vastly more complex functions. It's a key source of the model's deep learning power. Okay, so our vector has been expanded and passed through a nonlinear activation. The model has done its thinking. The final step is to bring this newly processed information back into the main pathway of the transformer. The vector is passed through a second linear layer. This layer's job is the reverse of the first. It projects the high-dimensional representation back down to the original D-model dimension. This is essential, as the output of this block needs to have the same shape as its input, making it ready to be fed into the next identical transformer block in the stack. So, to recap the flow for one token: expand, activate, project. Now, here is a critically important detail about how this FFN operates within the transformer. While the attention mechanism's entire purpose was to share information asterisk between asterisk tokens, the feed-forward network does the opposite. The exact same feed-forward network, with the exact same learned weights, is applied to each token's vector completely independently. There's no information sharing between tokens at this stage. You can imagine all the token vectors lining up and passing through the same processing station, one after the other, or even all at once in parallel. This combination of inter-token communication via attention, followed by independent, per-token processing in the FFN, is the fundamental rhythm of the transformer block, repeated over and over to build up a deep understanding of the input text. So far, we've treated the transformer block as a single, self-contained unit. We've meticulously unpacked its self-attention mechanism and its feed-forward network. But the true power of the transformer architecture, and indeed of deep learning, comes from what we do next. It begins with this block, the fundamental building brick we're now familiar with. The design is brilliantly simple and modular. The set of vectors that comes out of one block has the exact same dimensions as the set of vectors
we can simply
that went
stack
in.
them, one on top of the other,
Creating a
one
sequential
block can
processing
serve as
pipeline.
the direct input for
Each
another,
layer receives the
identical
output
block.
from the layer below it and passes its own output to the layer above. And when we talk about modern models, we build this stack deep. This entire stack of repeating blocks forms the core of the transformer model. The number of layers, often denoted by n, is a key hyperparameter that defines the model's depth. For example, a well-known model like BERT-base uses a stack of 12 of these layers, but the race for more powerful models has pushed this number to staggering heights. A large language model like the original GPT-3, for instance, uses an incredible 96 layers. This immense depth is a primary reason these models can build such a complex and nuanced understanding of language, moving from simple patterns to abstract reasoning. So, what is actually happening to our data as it makes this journey up the stack? Let's follow a single token's vector. It enters the first layer as a simple word embedding. Here, it undergoes its first transformation. The self-attention mechanism enriches it with context from other tokens, and the feed-forward network processes it further. This refined vector is then passed to the second layer. Here, the exact same process happens again, but this time, the layer is working with an already refined input. It's building upon the understanding established by the layer below it. With each step up this computational ladder, the vector's representation becomes more and more abstract and sophisticated. You can think of it as a hierarchy of understanding. The lower layers might learn to identify basic syntax and parts of speech. As we move up, the middle layers might start to piece together the meaning of phrases and clauses. And by the time we reach the top, the highest layers are capable of synthesizing information across the entire text, grasping complex ideas like causality, sentiment, and subtext. This final output vector is no longer just a representation of a word. It's a dense, information-rich embedding that has been transformed and contextualized by the collective processing of every single layer. This is the vector that holds everything the model needs to perform its ultimate task, generating the next word. And how it does that is precisely what we'll break down in the next scene. So far, we've taken our input tokens, embedded them into vectors, and passed them through a whole stack of transformer blocks. Inside each block, the self-attention mechanism allowed these vectors to exchange information and build up a rich contextual understanding. After the final block, we are left with a processed vector for each token in our input sequence. For generation, we are most interested in the vector corresponding to the very last token. This final output vector, let's call it v-final, is the culmination of that entire deep learning journey. It's a dense, high-dimensional representation that has distilled all the context from the preceding text. It is, in essence, the model's best guess, encoded in the language of numbers, about what should come next. But this vector, with its hundreds or thousands of dimensions, isn't useful to us directly. We need to translate it back into the world of human language, back into words. This brings us to the fifth and final major step in our process, unembedding. Now, this should look familiar. This is the very same embedding matrix, E, that we used back in step 2 to convert our input tokens into vectors. It's our model's dictionary, mapping every word in its vocabulary to a unique vector. To go in the reverse direction, from a vector back to a word, it seems logical that we would use the same dictionary, right? And that's exactly what the transformer does, with one elegant twist. Instead of creating a whole new set of weights for this step, which would be computationally expensive, it reuses the embedding matrix. To make the math work for this reverse lookup, we take that same matrix and we transpose it. This means we flip its rows and columns. This transposed matrix, E transpose, now serves as our unembedding matrix. This is a brilliant piece of design, ensuring that the space used for understanding words is the same space used for generating them, which enforces a powerful and efficient symmetry in the model. The process is now a straightforward matrix multiplication. We take our final, context-rich output vector and multiply it by this transposed unembedding matrix. The result of this operation is a new, very long vector. This vector contains the raw, unnormalized prediction scores for the next token. In machine learning, these raw scores are called logits. And how long is this vector? It has exactly one entry for every single token in the model's vocabulary. If the model knows 257 possible tokens, then this logits vector will have 257 scores. Each score represents the model's confidence that a particular token should be the next one in the sequence. A higher score means higher confidence. For example, if our input was the cat sat on the score at the index corresponding to the word mat would likely be very high. In contrast, the score for a word like xylophone would be extremely low. These logits give us the relative likelihood of every possible next word, but these are still just raw scores, not clean probabilities that add up to 100%. To convert these logits into a proper probability distribution from which we can sample our next word, we need one final, critical component. And that component is the softmax function, which is exactly what we'll explore in the next scene.
So, after that journey through the final layers of the transformer, we are left with this: a long vector of raw, uncalibrated scores that we call logits. Now, it's very important to understand what these are and what they are not. They are not probabilities. Notice how some values are positive and some are negative. If we were to add them all up, the sum would be meaningless. They simply represent the model's raw confidence for every possible token in its vocabulary. So how do we turn this messy list of scores into a clean, understandable set of probabilities for picking the next word? For that, we need a crucial final step: a function called softmax. The softmax function looks a bit intimidating, but it performs two very clever and simple operations. Let's break it down. First, for each individual logit, which we'll call z_i, we exponentiate it. That means we calculate e to the power of that logit. The mathematical constant e has a wonderful property. When it's the base of an exponent, the result is always a positive number, regardless of whether the logit was positive or negative. This single step elegantly solves half our problem by ensuring all our scores are now positive. Next, we sum up all of these newly exponentiated positive values. This gives us a single total number, a normalization factor. Finally, we divide each individual exponentiated score by this total sum. This normalization step is what guarantees that the final output values will all add up to 1. Let's watch this transformation in action. We take our input logits, apply the softmax function, and out comes a beautiful, clean probability distribution. The height of each bar now represents the model's calculated probability that a specific token is the correct next one. This output has two critical properties that make it a true probability distribution. First, every single value is now between 0 and 1. And second, if we add them all up, they sum to exactly 1. This gives the model a mathematically sound basis for choosing the next token. So, now that we have these probabilities, does the model just blindly pick the word with the highest score every single time? Well, not always. The way it samples from this distribution can be adjusted to make the model more creative or more predictable. This is controlled by a parameter called temperature. And we'll explore exactly how that works in the next part.
So, after passing through all the transformer blocks and the final linear layer, we have our list of logits, which the softmax function has converted into a clean probability distribution. Every single word the model knows has a probability of being the next word. Now, how do we actually pick one? The most straightforward approach would be to simply select the word with the absolute highest probability. This method is called greedy sampling, and while it seems logical, it has a major flaw. If you always pick the most probable word, the generated text can become incredibly predictable, repetitive, and frankly, quite dull. The model gets stuck in loops, choosing the same high-probability phrases over and over. To inject creativity and control the randomness of the output, we introduce a clever parameter called temperature. We apply temperature to the logits before they go into the softmax function. Mathematically, all we do is divide every logit by the temperature value, which we'll call T. Let's see what effect this has. A temperature of 1 leaves the probabilities unchanged, but watch what happens when we set the temperature to a value less than 1, say 0. 4. Dividing by a small number makes the differences between the logits much larger. This makes the resulting probability distribution peakier. The model becomes much more confident, almost exclusively favoring the word with the highest original score. This leads to more conservative and predictable text. Now, let's go the other way. What if we use a high temperature greater than 1? Let's push it up to 1. 8. By dividing by a larger number, we squash the logits closer together. This flattens the probability distribution, making the probabilities of different words more even. This increases the chance of selecting less likely words, leading to more random, surprising, and sometimes more creative output. But be careful, too high a temperature can lead to incoherent nonsense. For a good balance, let's set it to a common value like 0. 8. Okay, now we have our temperature-adjusted probabilities. We are still not going to just pick the highest one. The final step is to sample from this distribution. Think of it like throwing a dart at a set of targets, where the taller bars are bigger targets. The highest bar has the best chance of being hit, but it's not guaranteed. Any of the other words could be chosen, according to their probability. Let's see what it picks. And there's our choice. The model selects a human. This word is now considered generated. This entire process, from tokenization and embedding through all the transformer blocks to this final temperature-controlled sampling, is then repeated. The newly chosen word is appended to the input sequence, and the model generates the next word and the word after that, building up long and coherent text one word at a time. So far, we've broken down the transformer into its most fundamental parts. We've explored tokenization, seen how embeddings give words meaning, demystified the attention mechanism, and followed the data through feed-forward networks. Now, in this final scene, let's put it all together. We're going to watch the entire generative process unfold end-to-end to see how these individual components work in concert to create new text. This is the full generative loop of a model, like GPT. We can visualize the architecture as a cycle through several key stages, which should now look very familiar. It all starts with an input from a user, a prompt. Let's say our prompt is, "The laws of physics are." The model's task is to predict the next, most logical word. To do this, it first looks at the input sequence. The model processes this context and prepares to generate what comes next. The first step is tokenization. The word "are" is converted into its corresponding token, a discrete numerical ID. This token is now ready to enter the neural network. Next, in the embedding stage, this token ID is used to look up a dense vector of numbers. This embedding vector, which we've discussed at length, captures the rich semantic meaning of the token. It's no longer just an ID, it's a point in a high-dimensional meaning space. This vector, along with the vectors for the other words in the context, now enters the heart of the model. It flows through the entire stack of transformer blocks. Inside each block, the self-attention mechanism allows the vectors to exchange information, weighing the importance of other words like laws and physics to enrich the context of our current position. The result from attention is then processed by the MLP. After passing through many such layers, a final, highly context-aware output vector emerges. Now, how do we get from this processed vector back to a word? That requires two final steps. First, unembedding. The output vector is multiplied by a special unembedding matrix. This projects our vector from the model's internal size back out into a very large vector, with one entry for every single token in the model's vocabulary. These raw, unnormalized scores are called logits. A high logit score suggests a likely next word, but they're not probabilities. To fix that, we apply the softmax function. This squashes all the logit scores into a clean probability distribution, where all values are between 0 and 1, and they all sum to 1. Now the model has a clear ranking of the most likely candidates for the next word. All that's left is to choose one. In the sampling stage, we pick a token from this distribution. While there are many ways to sample, the simplest is to just pick the one with the highest probability, and in this case, the model predicts the word. Universal. And now for the most elegant part of the entire process, autoregression. The loop completes. The newly generated word isn't just the end of the line. It's appended to the input, becoming part of the new, longer prompt for the very next time step. The model now takes this entire new sentence. The laws of physics are universal, and performs this exact same loop again to generate the next word. And again. And again, building the response one token at a time. Each new word is conditioned on all the words that came before it. This simple, powerful, iterative loop is the engine that drives modern large language models. From a simple prompt, a coherent and contextually relevant stream of text is generated, all by repeatedly predicting just one word at a time. It's a remarkable demonstration of how complex behavior can emerge from a sequence of simple, well-defined mathematical operations.